Here we go over some common embedding algorithms and a TF-IDF vectorizer. So TF-IDF is often referred to as vectorizer. It stands for term frequency inverse document frequency. It's not exactly an embedding model because it does not actively form patterns or learn from the co-occurrence of words and their context. However, term frequency works by first identifying the number of times a word occurs across documents or texts or sentences, and then goes on to compute its inverse document frequency, which sort of gives more weightage to rare words. For example, let's say we're dealing with the compliance or legal domain. A word such as litigation or compliance might occur a lot because it's a boilerplate, and that is not going to be given too much weightage in the inverse document frequency step. However, let's say we have a pattern of cases relating to children or cases relating to a particular region, such as, let's say, Boston. Then those words might be given a lot more importance in the inverse document frequency stage because they are relevant to the current document at hand, but overall, in all of the documents we have, they're not occurring that much, meaning we have to focus on it a lot more with respect to this current document and give it a lot more weightage. And that's what happens in the TF-IDF stage, where we have term frequency multiplied by inverse document frequency, or term frequency into 1 divided by document frequency calculated per word. So stop words and boilerplate are usually made close to zero with this exercise, but in natural language processing, just going through a pre-processing stage of removing stop words, punctuations, and others are a good practice. Next up, we have word2vec. This is a very famous embedding model, and there is some actual active learning happening in word2vec through the use of a neural network architecture. And it learns in two different modes. One mode is the bag of words mode, where it establishes the likelihood or probability of a particular word provided its surrounding context. And this surrounding context is just taken as a bag of words without any ordering information between the words. That is, for word 2 to occur, word 1 must be present before it. And the other mode it works in is called skipgram, where the model learns the likelihood or probability of the surrounding context given a particular word. And here the order is respected by following a window-based approach, and the model is aware of the order of words within this window. So when the model learns to predict this likelihood, these likelihoods are then converted into a single vector using an activation function at the final layer called softmax, but there is no activation function in the inner hidden layers. And now, how does this even start processing words? Because the whole point of learning encodings or embeddings is because the algorithm cannot process text, but it can only process numbers, correct? So the input goes in the form of a one-hot encoding of the words, from which it learns to predict likelihoods in the bag of words format or the skipgram format, from which finally a softmax is applied to give a single vector with the dimensions you've specified, which serves as the embedding for the input document or the input sentence or input word. Next up, we have GLOVE. GLOVE stands for Global Vectors for Word Representations. GLOVE has a step before the learning phase, which is building of a co-occurrence matrix, which is built from the collection of documents or the corpus. So this co-occurrence matrix will help the model learn the probability or likelihood of a word in a context out of all the occurrences of the word. So here it learns the ratio of probabilities as opposed to raw probabilities. And building of this co-occurrence matrix and learning of the ratio of probabilities is usually more memory consuming compared to word to vec. But this is how Glau proceeds to learn a function that establishes the relationship between co-occurring words. Next, we have Elmo. Elmo stands for Embeddings from Language Models. Language modeling is just the task of learning to predict what the next word would be and with what probability or likelihood. And that's pretty much what Word2Vec did as well. Word2Vec was a predictive model, and Glove that we saw was a count based model. And within Word2Vec, we had bag of words where there was no order taken into account and all of the words were considered together. And then we had Skipgram, which actually had a window based approach where within the window the order was respected. Elmo just goes beyond that to learn words both before and after a particular given word by using a bidirectional LSTM. To understand more about what bidirectional LSTM is and where it can be used, I would again suggest my course Applied ML the Big Picture. But just note that this is what Elmo uses. It uses a bidirectional LSTM to learn both the word before and the word after, and Elmo sort of combines the hidden layer weights in a way where it helps it differentiate context and assign different vector values to the same word based on the context it occurs in or the surrounding words that occur along with it. Elmo and BERT are language models that perform these embeddings or come up with these embeddings, which can either be used as intermediate steps to more upstream tasks such as language translation, or it can be used for just classification, token level, or sentence level, and other tasks. Or these embeddings can be extracted from within and be used in combination with other algorithms and other natural language processing tasks. Now notice that Elmo is using a long short-term memory unit, which is sequential, and so it's not very parallelizable, which is when we can move on to BERT, which is a transformer-based model. Again, you can refer to Applied ML the Big Picture to understand where transformers fit in the bigger picture, but they are attention based, which helps them learn the importance of one word to another instead of having to process that sequentially. And for that reason, it's parallelizable. BERT follows an encoder decoder structure, and for our purpose of generating embeddings, we can use encoders to generate these embeddings. And just like Elmo, BERT can see both ways, learn to predict what's before a particular word and what's after a particular word. But if you think about it, we're already making a pass over the language in the language model in the forward direction. So wouldn't it be sort of like a cheating to try and predict in the reverse direction what you've already seen in the forward direction? So that's where BERT follows language masking, and it just masks up to 15% of the words at random. And sometimes it also follows random replacement to replace a word with another and to still try to be able to predict what the next word or the previous word is. So these are just some more advanced embedding algorithms or language modeling techniques that have been used recently. With that, you are now aware of some of the most commonly used embedding algorithms out there.